in this video, we will learn about the various ways in which we can assess the accuracy of a classification model. Specifically, in an accuracy, if we work with two classes, we might be trying to predict the probability of a person belonging to either class 1 or class 0. Now, the way we go about this is that we will run some algorithm which will give us a probability. We may get an answer like 0.67. Now, we do not know that this record will be class 1 or class 0. For that, we come up with a cutoff value. Let's say our cutoff value usually is 5 or 0.5. So any record above 0.5 will then be classified as belonging to class 1, and any record below 0.5 will be classified as belonging to class 0. Now, the big thing with this measure is that once we have come up with an algorithm and we have classified our records, how do we know that we've done a good job? How do we know that even if the model was relevant or needed, could we not just have guessed and then come up with the better estimation or as good a performance as some sophisticated model has given us? So for these reasons, we need to be able to start talking about how do we measure the accuracy of our predictions or our classification, what benchmarks we can use, not just to see how our model does compared to not having any model at all, but how our model does against other competing models as well. So two variables that help us look at these are accuracy and error rate. So error is essentially if a record belonged to class 0 and we classify it as class 1, then this is an error. Error could also be if a record actually belonged to class 1 and we classify it as belonging to class 0. So both of these will be errors. And if you look at the total errors as a percent of our total records, then we get the error rate. So error rate is essentially the percentage of errors we have made in our sample. So it is essentially the error over the total number of records times 100. Conversely, accuracy is defined as 1 minus our error rate. So from error we can move to accuracy, or from accuracy we can move to error. The naive rule says that you do not need any sophisticated model. Just look at the sample and see the predominant class in that sample. And then we can classify a new record as belonging to the prevalent class. Now, this naive rule may work in some cases, but it's still good to have some objective ways of assessing the accuracy of this model. We will also develop the idea of a lift curve, which tells us that, suppose our objective is to identify a high value, but a less prevalent or rare outcome. In that case, we might go with an algorithm that helps us target those high-risk groups, but may still have a higher error rate for the entire population, because our objective is not to fit or classify perfectly every single record, but to identify some of those high-value records. So for a model to work, there's a concept of separation of records. So a high separation of record means that the predictor that we use is able to correctly identify the high value classes so that we have a fairly low error rate in those. Low separation, on the other hand, means that the error doesn't do any better than what nature would say. So it is very hard to disentangle what records might be classified as a class 1 versus a class 0. So in other words, a low separation record would be when there is just homogeneity between our records and we can't really distill and make concrete classification of our sample. So one big tool that we will see which helps us study accuracy is what we call a confusion matrix. Now, the name may sound a little convoluted, but this is actually a measure of the classification performance of our algorithms. So read the rows as the actual class and the columns as what the model predicts. So for example, the first cell is what we call true negative. The record belongs to class 0 and the model correctly predicts it to belong to class 0. So this is actually an accurate prediction. And then the fourth cell, which is C11, is when the record is actually belonging to class 1 and the model correctly classifies it as class 1. So the way you read these numbers is that we always prefix the first number with what the actual class is, and the second number denotes what the predicted class is. So C10 is a record belonging to class 1, which the model incorrectly classified as belonging to class 0. So the accuracy then is the sum of our true positive and the true negative over our total records. Now notice that this is true negative and then this column is true positive. Then here we have a false negative and we have a false positive. A false negative is when the record belongs to class 1, but the model incorrectly says it belongs to class 0 or it's a negative class. So here I'm assuming that 1 stands for positive and 0 stands for a negative classification. So this false positive would mean that the model is calling it false, but positive, but it is false. So this record belongs to class 0, but the model is classifying it as belonging to class 1. So from this, we can get the overall error rate, and overall error rate is 1 minus accuracy. So if you subtract 1 from it, the total true positive, true negative get cancelled. We are left with false positive and false negative. And this is the variable that we had introduced before. Consider this confusion matrix where we have 3000 total records. And suppose we have true negatives amounting to 2689 and true positives amounting to 201. And then we have 85, which denotes our false negative. And we have 25, which denotes a false positive. Let us calculate the error and accuracy from this algorithm. So again, our overall error rate is our false negative plus false positive divided by 3000. So we have 25, which is our false positive, and 85, which is a false negative, and as a ratio of total observations. So our model's error rate is 3.67%. Then our accuracy can be given as 1 minus the error rate, or 96.33%. We could have also calculated accuracy as true negative plus true positive divided by total, and we would have gotten the same answer. So how do we go about classifying our records? Classification really is a two-step process. In the first process, and this is where some modeling is required, we're computing the probability of a record belonging to class 1. And once we have that probability, we come up with a cutoff value. Then you see that any record which was having a probability score above that cutoff value is classified as class 1. And any record that had a score below 0.5 or below a cutoff value is classified as class 0. Usually 0.5 is the most commonly used cutoff rate, but we can try with different cutoff rates, and often this choice is based on what our business question might be. In this visual, the first column denotes the cutoff rate of 0.5. So to classify an individual as an owner, we are looking for any probability score above 0.5, and that person gets classified as an owner. So if you look at record 14, the probability is 0.48, and this is less than 0.5. So this person is classified as not being an owner. However, if we change our cutoff rate, then our decisions may change. So suppose we lower our cutoff rate to 0.25. In this case, anyone with a probability score above 0.25 gets classified as class 1. So if we look at the same record, record 14, because 0.48 is above 0.25, we would now classify this person as an owner. We can also go up with our cutoff. In the third column, our cutoff is 0.75. With this high cutoff, we are saying that a person has to really have a very, very high probability value for us to classify that person as belonging to class 1. Now, in some business context, this may be a desirable outcome where you want to identify really your just very, very high risk agents or data points and classify them as class 1. So in this case, increasing the probability to 0.75. Now notice what happens to record 2. This record had a probability score of 0.56 and our cutoff of 0.5 classified this person as an owner. But if we increase our cutoff to 0.75, then this person gets classified as being a non-owner. And then the shaded areas or shaded cells tell us when our model got our predictions wrong based on what the actual class was. So the second observation belonged to class 1. The actual observation was an owner. And with a cutoff of 0.5, we correctly classified this individual as an owner. But with a cutoff of 0.75, we misclassified this person to belong to class 0 or be a non-owner. Our ultimate objective with these processes is to be able to see how we can get a better separation with a model compared to what nature may say. For this, we rely on an important concept called lift. Before we get into lift, let's see when this might be useful. Suppose our business problem requires us to identify class 1 with a higher priority. And some of the cases could be if you're trying to identify which of the records might commit tax fraud, which of the records might possibly default on their loan, which of the people would respond to a promotional offer. If we are seeing various signals and we want to detect a network intrusion, we might be interested in predicting delayed flights. So in all these cases, taken from different business settings, the interest lies in correctly identifying class 1 rather than class 0. So in these cases, the idea of lift or lift chart becomes very important. But before we get into that, let us look at some more measures of accuracy which will help us develop the idea of lift charts fairly intuitively. So again, going back to our table, assume that C1 is the important class that we are interested in. Sensitivity or true positive rate, as we saw, was the number of cases correctly identified as belonging to class 1 divided by the total class 1 cases. So now the C10 is capturing the number of class 1 cases that we misclassified as 0. And then C11 is the total number of class 1 cases. So this ratio or this true positive rate tells us if we classified a record as positive, what is the probability that that record is really positive? And we call this important measure sensitivity. So sensitivity is essentially our accuracy of identifying a model as true positive, or it's called the true positive rate. Specificity, on the other hand, is how accurately can we identify class 0 correctly. So to get specificity, we look at the ratio of true negative over all the negative classes. And that includes, of course, the true negatives, but also the false positives. So the negatives that were identified by the model as belonging to class 1. Now it is really important that we understand these two measures, so you might even want to pause here and kind of look at the formula here and then convince yourself and make sure that we understand that sensitivity is essentially the true positive rate and specificity is the percentage of C0 class correctly identified. So in other words, we're answering the question, if the model predicts a negative class, what is the probability that this class is really negative? Let's look at specificity once again. It is the true negative rate. We can from this also derive a really important concept called false positive rate. So false positive rate is essentially the proportion of predicted class 1s that were not class 1s. And we can get this by subtracting specificity from 1. So 1 minus specificity gives us the false positive rate. And we can see this here. Specificity was Tn over Tn plus Fp. So if we subtract this equation from 1, we will get C01, which is the number of records misclassified as class 1. And the denominator is the total number of 0 actual observations. So this is the false positive rate. Number of records incorrectly predicted as negative as a ratio of number of negatives. These two concepts, the false positive rate and the true positive rate, will be combined in a very important curve, which is often used to measure the accuracy of a classification algorithm. This curve is called the ROC curve, or the receiver operating curve. So this blue line, or the ROC curve, is actually showing us the various combinations of true positive and false positive rate for different cutoffs. So each point on this ROC curve is coming up from a different threshold. So the way we draw this curve is we vary the threshold from 0 all the way to 1, and for each threshold we plot the confusion matrix, and then from the confusion matrix we calculate the true positive, or the sensitivity, and the false positive rate, or 1 minus specificity of our model, and we plot each of these points, and joining these points we get what we call the ROC curve, or the receiver operating characteristic curve. The accuracy of a model can be assessed by how far the ROC is from the 45-degree line. The 45-degree line essentially tells us how a naive classifier might do. So each point on the 45-degree line has the same true positive and the false positive rate. So it's like a toss of a coin to assess what the outcome might be. Contrast that to a perfect classifier. A perfect classifier will correctly identify all the true positives and have no false positives. So this point would be for the perfect classifier. And if we look at the ROC curve for a perfect classifier, it would be like this triangle. The model's ROC that we get can be then compared to this diagonal line and this upper triangle. The closer the ROC curve is to the upper triangle, the precise or the more accurate the model is. So we can look at the area under the curve. We call this AUC of the ROC curve, and AUC equals 1 for a perfect predictor. So if the predictor classifies our outcomes correctly, then the AUC, the area under the curve, would be 1. So greater the number or area under the curve, the better the classifier is. The naive-based model would have an area under the curve equal to 0.5. And any model that does worse than naive rule would have an AUC less than 0.5. So this area under the curve is a very good metric to look at the accuracy of a classifier. There are two other measures that can be used to assess the accuracy of a classifier. And these two measures are precision and the F1 score. Precision is essentially, of all the cases identified by the model as class 1, how many were correctly identified. So the denominator would be all the C11s and all the cases that were false positive. So this is, the model said these things are positive. Out of these positive, how many were actually positive? Now this looks similar to sensitivity, but there's a slight difference. For sensitivity, we're looking at what is the correct identification rate of all our positives. So our C11 as a ratio of C11 plus C10. So how many were actually positives, but the model called negatives. So this is our sensitivity. our precision is C11 as a ratio of all the positives that a model called. So that could include false positive as well as true positives. These two measures, precision and sensitivity, can be combined into what we call an F1 score. And for some algorithms, one quick way to assess if a model does better than the other model would be to check the F1 score. And F1 score is given as 2 times true positive divided by 2 times true positive plus false positive plus false negative. So this F1 score or FME score is a summary measure which is a combination of precision and sensitivity and provides us a way to measure competing algorithms. So an algorithm which has a higher F1 score would be doing a better job at classification of the class 1 outcomes than another algorithm which may have a lower F1 score. The final measure we will look at in assessing the accuracy of a classifier is lift curve. A lift curve essentially poses the question that for a given proportion of our data, how much better does a model do than having no model at all? So we are looking at the lift or the increase in prediction using the model compared to no model. The intuition behind lift curve is that once we have come up with the classifier, we assign probability scores to our records. Let's sort our records in descending order. Once we do that, we get something called a cumulative lift chart. We compare the actual class 1 observations identified by our model compared to the number of actual class 1 observations identified if randomly selected. What that means is, let's say I'm looking at the top 10% based on probability scores. So suppose my sample has 100 people. The top 10% or decile would be 10 people. Also, to keep things simple, let's assume that our class 1 prevalence rate is 10%. So if I randomly choose any 10 people, no model says that out of these 10, one person should belong to a class 1 because our prevalence rate is 10%. So this should be the same no matter what 10% or 10 people I choose. So now suppose we pick the 10 highest people in terms of the probability scores. So the probability score based on the model is the highest for these 10. Randomness says that out of these 10, no matter what the probability score is, only one person will respond as class 1. However, now suppose that in these top 10 people, we have correctly identified 5 people belonging to class 1. So our model is doing actually 5 times better than what randomness would say. Now let's look at the next 10 people. Suppose in that next 10 group, we correctly identify 4. Randomness would say out of those next 10, only 1 would be class 1. So now our model is doing 4 times as good as nature would in this second batch of 10 people. So the lift chart is essentially looking at the percentage of correctly identified as a percent of what nature would say. So we're looking at a multiple of how many do we correctly identify versus what the randomness is saying. What we have here is an example of a lift chart. So here, consider 30th percentile. At this, and again, these percentiles are ranked based on their probability. Of the 30th percentile, our lift chart being 2 means that our model is currently able to identify 2 times as many class 1 cases as what no model would say, or the baseline would say. So you want to look for a model which has a fairly high lift for at least the initial few decile of your data. So then you're able to correctly identify the people who have the highest propensity to belong to class 1. A practical application of this would be that let's say that you want to send mailers to those who are more likely to respond to your campaign. If you have built a model and the model has a fairly high lift on a validation set, then we know that based on these algorithms, if we get new data, we can then come up with a probability score, and we will send the mailer to only the top 30 percentile of people based on the probability score. And we can expect a lot of plus responses from that sample that we have chosen, rather than if we were to randomly choose the same number of people from our data set without doing any model.